Okay guys, mass spec, hopefully you've been watching the video. We can work these problems here. We're moving along, yeah? Okay. In 2 weeks we'll be completely done. We'll be starting a new summer session if you're taking the second summer session. It starts 2 weeks from today. We'll be long done in 2 weeks. Okay? Another week, 10 days. Well, gotta pull through. Okay, let's work these problems here. Which compound goes with which mass spectrum? I assume you've been watching video, reading your textbook about mass spec. I would start by saying, what type of cleavage do we expect here? Because if you add these up, they're all 88. Molecular weight of each of these is 88, and each mass spec shows an 88. So we have to look at cleavage peaks. Where do we expect this to cleave at? Major point is carbocations. Basically we form cation. What's the best type of cation? Tertiary. What's another way to, well, how else can you stabilize a cation? Resonance. Okay, we're looking for the best cations. Alpha cleavage. Alpha cleavage is cleavage next to what? Cleavage, you put the cation next to what? Lone pair of pi bond. Alpha cleavage. Okay, where can this cleave? We can do alpha cleavage here. That would give boom, boom, O-methyl. And we're going to make cation here. Radical cation can cleave. When the radical cation cleaves, it forms what? A radical and a cation. Here's the cation. What would the radical be? Just a CH3 radical. Alpha cleavage. We put cation where? Next to lone pair. Why? Because this cation is stabilized by resonance. We can draw a resonance structure. These electrons move in, make pi bond. Yeah? I'm not going to show resonance structure, but it's resonance stabilized. What's the mass of this? Whatever that is M. We know it's 88, but it's M minus what? What did we cleave off? 15. Now, 88 minus 15 is what? 73. All right, we can also cleave here and make the same cation. We can also cleave there and make the same cation. So cleavage here, 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 it's all the same thing. Nothing different. Up here, alpha cleavage would involve cleaving a what? That's a CH3. You cleave just a, if you cleave a methyl, you won't have a cation next to an oxygen. You will have nothing over there. What do you need to cleave to have a cation next to oxygen? H. And that would be loss of 1. Okay? Now, that is possible. Typically, we're going to show cleavage of carbons. It is possible to cleave an H here and show an M minus 1. Alpha cleavage up here. We cleave here. We get boom, boom, O-methyl, cation there. Why? Resonance stabilized plus what? CH3 radical. What's the mass of this? Same thing, right? These have the same mass. This is also 73. We can do another alpha cleavage up here, though. Could we also cleave over here? And that would give that cation plus what? Plus an ethyl. Plus an ethyl radical. What's the mass of this? M minus what? 29, which is what? 88 minus 29 equals 59? 59 expected here. Alpha cleavage up here gives 73 or 59. Alpha cleavage down here only gives 73. Alpha cleavage up here, this side you cleave an H, let's not do that, let's cleave over here. Let's cleave there and get a propyl radical plus what? A cation next to a lone pair. Resonance stabilized. This is M minus what? What's a propyl? I think it's 43, isn't it? 3 carbons is 36. How many H's on that? 7. M minus 43. What's 88 minus 43? 45? Up there we expect a 45 from alpha cleavage. Did we expect 45 here? No. Let's look at the mass specs. What does the first one show? It shows base peak at 73. Do we expect a 73? For which one? The last two. This does not appear to be the first compound because we didn't expect a 73. We also see a 57. You got to be careful. The textbook is labeling these for you. I'm not going to label these for you. It's like a neon light. What is 57? It's also 31. Do we expect a 57 for any of these? Actually, we did not expect a 57. Did we not? We'll have to go back to that. Maybe we could think about something else over there. What's the next spectrum look like? We got a base peak of 59. Did we expect a 59?
Yes.
For which one? Second one. We've also got a 73. Did we expect a 73?
Yes.
For which one? Second one. Again, I'm not going to label these peaks for you. You're going to have to recognize these peaks on your own. Indeed, we could go through this and then come back and look again, but indeed, the second spectrum is the second molecule. Because what we expect is here. And it's not in the other two. Do the other two show a 59 or 73? Actually, this one shows a 73. But it doesn't show a 59 like this one does. I'm sorry. It's 73, but that one doesn't show 59 like we predicted for the second one. How about the third spectrum? What does it show? Base peak of 45. Did we expect a 45? Which one? First one. Did we expect a 45 for the other two compounds? No. First compound is the third spectrum. We expected 73. And 59. It's here. Second compound is the second spectrum. That means the first spectrum goes with which compound? Third one. We expected a 73. It's there. What is the 57 though? Now the textbook labeled it, makes it look like it's important. I mean, why is it more important than this one? But again, you're going to have to determine that on your own. But you do see a 57. We can also look at structure. Is there another cation we could form in compound 3 that is fairly stable?
Yes.
Yes. Instead of cleaving here and doing alpha cleavage and leaving cation and leaving, no, instead of cleaving here, alpha cleavage leaving cation next to lone pair, where else could we cleave? We can cleave here. And here leaves a cation over here and make an oxygen radical. Cleavage of radical cation gives a radical cation. And we can see this cation being formed. Why? What's so good about that cation? It's tertiary. It's a pretty darn good cation. It's not resonance stabilized, but it is tertiary. What's the mass of this? C4H9, which is what? 48 and 9? 57. Top spectrum has the additional peak at 57. So you're predicting cations, and then you're looking for where they're at. Again, the mass of all these are constitutional isomers. They all equal 88. Every one had a molecular ion of 88. Molecular ion of 88. So that's not going to help you. Molecular ion of 88. If those had different masses over there, then you wouldn't have to look at cleavage. You could just look at the molecular ion. That would be quite simple. Typically with mass spec, you are asked to look at the cleavage peaks. Doesn't mean you have to. I mean, it depends on what you're doing and what the choices are. I mean, in this example over here, where I coupled GC with mass spec, this came from the research lab. You're interpreting a GC mass spec for your group report that's due Monday. The GC shows 4 components. 1, 2, 3, 4. These two being sort of predominant, that one being major. We get a mass spec of each of those. They're all here. Actually, only 3. Mass specs for A, B, and C are below. I'm not giving a mass spec of that. I'm not sure why, but I could have, but just those 3. Basically because we never figured out what that was, and maybe there was not enough room here, I don't know. But A has a mass of 293, B has a mass of 255, and C has a mass of 237. And from that, we can tell, this was a fluorination reaction, we can tell that 293 had 3 fluorines added, because that adds up to 293. 255 had only 1 fluorine added, and 237 is where no fluorine added. And actually the 237 molecule was the starting material for the reaction. We started with that pure, tried to fluorinate it, and ended up with this mixture as the result. A lot of starting material remained. We did create 2 new products, monofluorinated and trifluorinated. Also created this as some type of side product, minor impurity, and I don't know that we ever figured it out. In this particular chemistry, we had trouble getting the starting material to fully react. It was always there after the reaction, no matter how long you did the reaction. Just sort of, it's always incomplete. But we were trying to monofluorinate, trying to make this. What we discovered is that we're actually also got some trifluoro. Right there. How do we know it's trifluoro? Well, you can look at the mass, and it adds up to having 3 fluorines added. Could it be something else? Well, I mean, it could be. I mean, if you combine eggs, sugar, and flour, you're probably going to get a cake. So there's some expectation that you can cake. It'd be kind of odd if you combined eggs, sugar, and flour and ended up making an automobile. Okay? So we kind of have some clue of what we're going to make. That comes from just knowing your chemistry. But we can also analyze this another way. For example, you can get fluorine NMR, and fluorine NMR showed that it had 3 fluorines. There's other things you have to do. Well, how do we know the fluorines are here and not somewhere else? Well, there's other analyses you can do. What does the mass spec confirm? The mass spec told us there were 3 fluorines there. Ultimately, we had to separate all this by tedious separation, and then you run a GC mass spec, and the only thing in the GC would just be that, and now you say, hey, now we have a pure compound. A lot of work to get to that, though, tedious separation. But in this case, we never had to look at cleavage. All we looked at was just the molecular ion. Okay? So it's different. Over here, it's a nice pure GC. Look at that beautiful GC. 1P. Very pure. And here's the mass spec. Molecular weight is 337. And look at the beautiful molecular ion peak there. 337. Yeah. Confirms mass. There's some cleavages there if you want to try to get into thinking about what the cleavage could be. You know, you got a new molecule, you got, okay, how's this thing going to cleave? Well, one way it could cleave is the CI bond could cleave. And what's the mass of iodine? Like 120 something? You cleave 120, you're going to get about 210 or so. That's where the iodine radical is cleaved, and you just end up with cation here, and that adds up to 210. So that's sort of easy to come up with. What are the others? The base peak is actually 164, or whatever that is. So you have to think and study. When you make new molecules, you're not always going to have, you know, something in the textbook telling you what it's going to do. What is this peak at 338, which seems to be 338? What is that? Because the mass is 337. What is 338? I discussed it in the video, I'm sure. 338? I'll let you figure that one out when you watch the video.
Is it an isotope?
What?
Isotope?
Isotope of what? But an isotope is...
So it has a higher or lower molecular weight, but it goes between 2 different molecules.
Yeah, but what is it? You said that. You mean the molecule?
Yes,
Isotope of the molecule?
yes.
Well, isotopes are not of molecules. Isotopes are of atoms. So what particular atom are you saying there might be an isotope of? Because we have carbons, nitrogens, hydrogens, and iodine. What's the isotope that is? Carbon. And what's the major isotope of carbon? 12 is the most common. You add that up, it's 12. Whole numbers, we're just using 12, but carbon can also be 13. We said this on day 1. What's the percentage of C13 naturally? About 1%. 1% of the carbons in your body are C13. 99% are carbon-12. Okay? In this sample, 99% of the carbons are carbon-13. 1% are carbon-12. 1% are carbon-13. If one of the carbons is a C13, the mass is going to add up to 338. This is where one of the carbons in the molecule is C13. What if the molecule had all C13s? Well, that ain't very likely because there's only 1% abundance of carbon. What's the chance of all of them being C13? No. Good chance of there being 1. What's the chance of there being 2 C13s in this molecule if naturally only 1% are carbons? There's actually math you can do to calculate that. It becomes quite low. And see, it depends on the sensitivity of your instrument. Is there a peak at 339? It becomes quite low and you may not be able to see it. The resolution may be too low. What's the chance of there being 3 carbon-13s? It's getting quite low. So low that the instrument can't pick it up. Okay? because it's maybe only one out of a gazillion molecules have repeat, okay? It depends on the sensitivity, but usually you get a peak for at least one. Yeah, it's in the video, yeah? Okay, a little bit of mass spec. You will be on the quiz tomorrow. There's problems in the workbook. Any last questions there today? Substitutions. Nucleophiles. How do you judge strength of nucleophiles? We mentioned sterics around the electrophile thing with the leaving group. Can sterics affect the other reactant, the nucleophile? Well, yes. Sterics can affect either reactant. These amines. Amines can be pretty good nucleophiles, even though they're neutral. Just like they can be pretty good bases, even though they're neutral. Which is the best nucleophile of these three? Primary amine. That's better than secondary, and that's better than tertiary. Why? Because as you start putting these alkyl groups around the nitrogen, okay, I have to go over here and do a backside attack. All right? Right? Ooh, a carbon with a leaving group. Ooh, a partial positive carbon. Ooh, I'm attracted. Okay, here I come. And boom, backside attack. Okay? What if I start having substituents? Ooh, ooh. Uh-oh, sorry. Uh-oh. You know, then you, I forget about it. Okay? It's harder, right? You got these wings here. And it starts, that's called steric congestion or steric interference. Okay? It's just crowding. The more crowding you have around your lone pair, which is the reactant, the business end, right? And in fact, tertiary amines are known to be non-nucleophilic. They're actually used in elimination reactions as non-nucleophilic bases. It causes important distinction between nucleophiles and bases. Nucleophiles are hurt by sterics. Bases are not. Why? Because when something attacks an H, the H is so small that the sterics of the base doesn't matter as much. But more importantly, there's a difference between how you attack an H and how you attack a carbon with a leaving group. How do you attack a carbon with a leaving group? Backside. Okay? So backside, it's like, here I come, but it's more than that. I got to go around to the backside. And that's, I got all these wings, and so I can't get around to the backside. Now, of course, it could be here, but it could also be turned around, and that's going to slow the rate down on average. Well, how do you attack an H? Well, an H is a 1s orbital, and it's spherical, and you don't have to attack backside. So you can attack either way, and it's like, boom, there you go. And so you didn't have to maneuver as much. But the maneuvering with sterics becomes really difficult. It's like, I can't maneuver as much for backside attack. Attacking an H is easier. Sterics, usually you don't need to discuss sterics with acid-base reactions. So, this remains a decent base, because sterics doesn't matter that much. But it becomes a bad nucleophile, because sterics do matter with nucleophiles. This is substitution on the atom that's the nucleophile. You can also have substitution next door. Look at these oxygens here. They're all minus, yeah? 3 lone pairs. This is a better nucleophile than that. That's a better nucleophile than that. Well, every one is just one alkyl group on the oxygen. The difference is next door. The carbon next door is becoming more substituted. Well, that matters as well. So the one on the right is also sterically congested.
It may not be quite as bad as this, where the groups are adding to the exact atom. But adding next door is also a major effect. And so we see that as steric crowding. Nearby the oxygen, and again, I'm telling you, it can affect even though it's not on the oxygen. This is called tert butoxide. Oxide, and over here we have a tert butyl group, right? So it's called tert butoxide. Sometimes you just see it called T-butoxide. And T-butoxide is a fairly common non-nucleophilic base, because the crowding makes it less nucleophilic. Now I'm saying these are non-nucleophilic. That doesn't mean they can't be a nucleophile. They're less nucleophilic. It's just like a non-stick pan. Does anything ever stick to a non-stick pan? Sometimes it does, okay? So I don't want you to say, I thought you said it couldn't happen. You know, well, I'm telling you it's hindered. Hindered is sometimes the word used. A hindered nucleophile. Yep. All right, because of sterics. This should just tell you the difference between acid and base. I've already told you that. I mean, between nucleophile and base. I've already discussed that. Resonance effects. This is a better nucleophile than that. Why? Okay, resonance, right? Well, what do you know about the difference in these electrons here? These electrons are sitting right there on that oxygen. They're not delocalized. There's no resonance. There's no p orbital next to them. What do we know about this? Okay, can we do resonance? Electrons here, electrons here? Yeah? I reckon I'll do the resonance. You can draw it close as you want there. What do we now have? Oxygen minus. Double bond here. Yeah? What's the true structure? A blend. Anytime you have resonance, the true structure is a blend. Delocalized bonding. The blend is what? Bond and a half, bond and a half. What's the charge on this oxygen? Partial minus and partial minus. So, we drew this as a minus. Is it really a full minus? No, in real life, it's really only a partial minus. So which is going to be more attractive to a partial plus? Okay? Right? You don't have to draw every single thing here. You got it. You got a partial plus. Which one of these is going to be more attractive to it? Full minus or partial minus?
Full minus.
Full minus. There's a better nucleophile, as we said. Basically, if we delocalize the electrons, it decreases the electron density here. The nucleophiles need to have high electron density. Nucleophiles like what type of charge? They like the nucleus, and the nucleus is positively charged. Again, you can call a nucleophile a positive phile if you wanted. We don't use that term. Which is going to like a positive charge more? That one is more of a minus. We've got to recognize that this has resonance and it's really a partial minus. Okay? By the way, what is the name of this molecule? We should have learned it in Gen Chem. Name of that molecule. Anybody? What? A carboxide? A carboxide, that's not a word. Because it's an anion of a carboxylic acid?
Yeah.
That's called a carboxylate. You're close. Ide is an anion. It's called carboxylate. Carboxylate anion. Okay, but what's the name of that particular one? If there was an H on that, what would that be called? But specific name. No, it's not an aldehyde, it's carboxylic acid. Okay, you put it on your salad, you mix it with some other stuff and a lot of water. You put it, yeah, vinegar is 5% acetic acid, yes. Acetic acid. What's the anion of acetic acid called? Acetate. Okay, now we're getting somewhere. You should have learned acetate in Gen Chem. Okay, acetate is abbreviated like this. Okay, that's because this is acyl. What is an acyl group? An acyl group is a carbonyl, okay, with a methyl. There you go. Oxygen, carbonyl, methyl. This is minus. That's what, yeah, looks familiar? It should. Acetate. Okay, the acetate anion is not as nucleophilic as this. What do you want to call this? That's an ethyl group on an oxygen. If there was an H, we would call it hydroxide. What do you want to call this? Okay, I thought I heard something else, but you're saying yeah, the ethoxide anion is more basic than the carboxylate or the acetate specifically in this case. Okay, a little bit of nomenclature for going forward, particularly where we have two, but you should have known acetate already. Acetate right here. Acetate where one of the carbons is carbon 12. Remember I showed you, carbon 11. Okay? Carbon 11 acetate used for PET imaging of prostate cancer, and right there is prostate cancer being imaged. Okay, using acetate where one of the carbons is carbon 11, which is a positron emitter, and you can do positron emission for scanning there. All right, and showing up is the yellow there. Prostate cancer. Acetate. You guys know acetate, right? Okay. Which is more basic over here? This is called cyclohexylamine. What is this called? We know this one. Aniline, which is more basic. Well, obviously this one. Why?
Because it doesn't have
this lone pair is in a p orbital. What do we say about lone pairs in p orbitals? Typically not basic. They're busy doing what? Resonance, delocalized. That nitrogen has less electron density because the lone pair is delocalized. Resonance, okay. Hybridization effect. A lot of this mirrors the acid-base handout we had. Okay, because nucleophiles and bases are very similar, except for one major thing being sterics. Nucleophiles are affected by sterics. Otherwise, it is often the same argument. High electron density makes a better base. Which one's a better nucleophile here? Obviously this one. Why? This lone pair is in what type of orbital? sp3. This one is in what type? What type? Not a p orbital. sp2. You need to know that. If you graph it, you're going to see it's sp2. Which one is better? More S character. What does more S character mean for the lone pair? No, the lone pairs aren't acidic. There's no H there. Better parent. More S character, closer to the nucleus. Held closer to the nucleus. Thus, it's not going to be able to go do a backside attack as well. Okay? You could say it's a better parent. Nitrogen's not as good as a parent. All right? It lets its kids get out there and do backside attack and stuff. All right? Rank the following according to nucleophilic strength. What's the strongest nucleophile here, number one? These look like minus, 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 right? That one's neutral. What can we say? Or we can do the opposite. Can you identify a weakest one or anything?
weakest nucleophile?
Yeah, neutral. This says from strongest to weakest. Strongest would be 1, weakest would be 4. I think that's 4. What's next? Both of these are oxygen anions, right? Which one's stronger nucleophile? No, acetate, the oxygen's delocalized. We just looked at acetate for about 15 minutes. Acetate's weaker than this. This is not delocalized. It means this is stronger. So that means this, well, we got to look at this one first. But of these two, hydroxide is stronger. Compare this. This might compare best to that one. Which is a better nucleophile? Sulfur. Why?
It's more bigger size.
Larger, sulfur's not as good a parent, doesn't hold the electrons as tight.
That one's better than that. That one's better than that. The answer is 4, 3, 2, 1. The sulfide, sodium sulfide, is a better nucleophile. The body actually uses sulfur as a nucleophile, so we'll show that a little bit later. How about the next series? What's the best or worst? Can we... Well, how about the first two? This looks very like we can maybe compare these. F minus or Cl minus?
CL is bigger than F.
F holds the electrons very tight. It ain't going to let those kids out of the house. Okay? That's a better nucleophile. Let's go over here. What about this? Well, how about these two? They're both oxygens. Which one's better? O-methyl or O-T-butyl? O-methyl. O-T-butyl has steric hindrance. Steric hindrance. So that was better than that. We need to kind of look here, though. Which is better? O-methyl or that? The two best of these two. Which one's better? Actually, O-methyl, because chlorine is more electronegative. Although we're going kind of diagonal. I would consider anything over here more electronegative than anything over here, even though we're going down. And it may not even be right, because I may not be as electronegative as O, but since you're going this way, you also have size. And because of the size difference, you can consider these all just more electronegative. It will give you the right answer. All these are more electronegative than O. That gives you the right answer, even though. Okay. No halogen is going to be a better. I'll take some of that back. When you're going, what do you call that? Diagonal. It can be a little bit apples and oranges. I want to take a little bit of what I said back. Because I was sort of relying on base. Nucleophiles can be a little bit different. In the end, which is a better base? It's the oxygen here. Chlorine's more electronegative. Sort of like this. I said base. We're talking nucleophiles. In terms of bases, it should be easy. O-methyl is the same as OH. Which is a better base? Hydroxide. You put a methyl on it, it's really no different. Not much. It's actually a little bit stronger base now because the methyl donates. But if that's a stronger base, it should also be a stronger nucleophile, unless this adds a lot of sterics. But a methyl is not a lot of sterics. It's also a better nucleophile. That's better than both of these. That's better than that. This can be a little bit, you got multiple things going on here. How about the one on the end? What's the charge of nitrogen? Negative, right? Because the potassium's positive. Okay, this is an NH2. We've seen this before. That's actually formed in the dissolving metal reduction of an alkyne to a transalkene, right? It uses a strong base. We use this base to deprotonate terminal alkynes. Pretty strong base. A neutral nitrogen is a pretty good base. These are also good nucleophiles. There's no sterics here. This should be a pretty good nucleophile. How does it compare to O minus? Should be better. At least O is a better parent. This is the best. That's the best. Next is going to be an oxygen. Which is better oxygen? Which is a better nucleophile? This. Because it's less sterics. That would be 3. That's where it could be tough. You could say, well, will sterics make it worse than these? That's where it can be a little bit tough. What's the worst? This. I would rank them like that. Sort of just saying that an O minus is going to be more nucleophilic than a halide. But of the O minuses, we know that this one's better than that one because this one does not have sterics. Remember, those are ranked according to atom type. An atom type should give you this. Then you have to distinguish between the same atoms by looking at sterics. Summing it up, what type of nucleophile can participate in an SN2 reaction, which requires backside attack, kicking off the nucleophile? What type of nucleophile can participate? It's on the next side. Page. What type? Only strong ones. Let me ask you a question. Is the nucleophile involved in the rate determining step of an SN2? Yes. Okay, you need to be able to answer such questions. Yes. What is the rate determining step? What's involved? Yes, nucleophile is involved. The rate determining step is the hard step. The nucleophile is involved. For it to be involved in the hard step, it has to be strong. If it's weak, it can't do a rate determining backside attack. It has to be strong. Okay? Well, what are strong ones? Very similar to bases. In general, only anions and sp3 amines are strong nucleophiles. But you got to be careful with that general statement. A halide, according to that first statement, F minus would be classified as a strong nucleophile. But no, halide is not. I should put here some, because that's not a strong nucleophile. But what do we know about I minus? I minus is actually a decent nucleophile because it's so big and the iodine is not as electronegative. Okay? So big difference in nucleophilic strength here that was shown before. So we got a general statement, but you got to be careful. You remember when we did hydration of alkenes, and we generated maybe a carbocation because we were using H plus and HSO4 minus. And then what attacked the cation when we hydrated it? Water. And water acted as a nucleophile. Why did this not attack? Why come that didn't attack? Because it's a... Because of what? Why did we have certain acids that we use? What did we say about this conjugate base? We said it would never attack. Why would it never attack? Because it's a lousy nucleophile. Okay? But I thought you said anions were strong. I did, that's the opening statement, but I also told you this. Highly conjugated anions are not that strong. Highly conjugated. Okay? Basically, okay, highly conjugated, that's why it never attacked. Halides, okay? So the opening statement is, in general, anions and sp3 amines, but there are exceptions. That and that are not good nucleophiles. That's why we used HF and H2SO4 as certain acid catalysts when we did not want the anion to attack anything. But if you use HBr, the Br minus will attack. That's because Br minus is a decent nucleophile. Which compounds below are strong? Nucleophiles. Is this a strong nucleophile? Is it an anion? Is it an sp3 nitrogen? No, not strong. This one. Not strong. Next one.
Yes.
Yes, strong. It's an oxygen anion. How about the next one? Strong. It's an sp3 nitrogen. Good nucleophile. Next one. No, lone pair is conjugated, not as nucleophilic. How about this one? What is this? What's the charge of the CN altogether? Negative, because K is plus. What is CN? What would be the structure? Structure is that, because CN has 10 valence electrons. This would be a blue structure for it. That carbon, both atoms have octets. That carbon has a minus charge. What do we call that? Cyanide. That's potassium cyanide. That's one of my favorite reagents, KCN. Anybody familiar with KCN? Anybody familiar with the band called KCN the Sunshine Band? Anybody? Y'all don't know KCN the Sunshine Band? Okay. From the 70s. It actually came to Augusta in the fall. It's KCN the Sunshine Man. That's why I like KCN so much. Okay. Cyanide's a very versatile. It's a good nucleophile. It was circulated? Carbon, it's an anion, right? It's carbanion. It's carbon nucleophile. Carbon is an anion there. You don't often find carbon as an anion. But it's bad. KCN's pretty cheap. Or sodium cyanide, potassium cyanide. Cheap, lots of chemistry you can do with it, very versatile. The only problem is it's highly toxic. I mean, it will, quite toxic, deadly toxic. Okay, so we have to be able to judge what are good, strong nucleophiles, and that's what we just did because SN2 requires one. At this point, we're going to look at some specific SN2 reactions. Now, I'm saying SN2, we're kind of focusing on SN2. We'll go back and pick up SN1. We may see some SN1 here along the way. Many of these are SN2 reactions, though. The first one is alkylation of oxygen. Alkylation of a carboxylic acid, a way to make an ester. First off, we're going to alkylate this oxygen here by doing an SN2 and attacking a carbon, putting the carbon on here. Is this a good nucleophile for SN2? No. Can we make it a good nucleophile, though?
Yes.
If we deprotonate it and make the anion, is this a good nucleophile?
Yes.
It is. It's an anion. Now, you might argue that, but isn't it delocalized? Yes. But it is an anion. It's a decent nucleophile. Now, it's not as strong as something that is not delocalized, but it's still itself a good nucleophile because it's an anion. What reagent would do this? Give me a reagent. Because as we move along, we start doing more synthesis. You have to know reagents, propose reagents. What would do this? In general, what do we need to do this? What do we need that will remove an H? Okay,
NaOH.
that will work. Yes. Why did you choose NaOH? Because you need a base to remove an H. You got an acid, you need to deprotonate it. Bases deprotonate things. Could it be something other than NaOH? It could be a million and one things. For example, it could be KOH. It could be lithium hydroxide. You could use something other than hydroxide. You could use potassium carbonate. You could use sodium bicarbonate. You can use them, there's a million and one bases. Okay? You could even use something like triethylamine, because amines can act as bases. You need a base. Your choice. What's your favorite base? We'll go with sodium hydroxide since it was suggested.
Can you use water?
No, water's not a base. You put acetic acid in water, will it completely ionize? No, that's the definition of a weak acid. It's a weak acid. And if you look at that equilibrium, only like 1 out of a billion ionizes. We want complete formation of the anion. We need something that will completely do this. We can judge this equilibrium. This is pK of what? Carboxylic acids are about 4 to 5. What's the acid over here? Doesn't these react to make sodium acetate plus water? What's the pK over here?
16.
16. Which side's favored, 5 or 16? 16. Yes, hydroxide will work. If you do water, you're going to have to show hydronium ion over here in this form. Then it's going to be 5 and -5. Which is favored?
5.
Wrong side. All right. Okay, now that we have acetate here, the anion, the carboxylate anion, we can come in here with a carbon with a leaving group and bam, backside attack, kick off that bromine. What bond are we making? O to the carbon? Right there. We just made that bond. Because under my hand used to be a bromine, but now it's what? The nucleophile. It replaced it in a substitution reaction called an SN2 mechanism. Is there any intermediate here? No, it's a concerted backside attack, kick off leaving group, make this bond. If we balance this out, what can we show over here? How about sodium bromide? Isn't there a sodium ion here? We made water, but also, so you can show something like this. The acid is now what? An ester, right? We alkylated the oxygen. Alkylation of carboxylic acid. It's a common and easy way to make esters. Yep. We can also alkylate alcohols and phenols. Thanks for suggesting sodium hydroxide so we can keep it consistent. You could have suggested cesium carbonate. That would have worked as well. But then we would have had to switch to a new base down here. Because down here I showed sodium hydroxide as a base. Well, sodium hydroxide worked down here. Apparently not, right? Why not? Well, alcohols have pKs of about 16. If we use hydroxide, we would make the sodium alkoxide plus water. That has 16. Which side's favored? Neither. That's a perfect equilibrium. And if neither side's favored, it's not going to work in practice. You need to have your side favored by about 2 to 3 pKa units. I'm not going to explain further why. You need, okay. Up here we went from 5 to 16. That was a difference of 11. All right? It's no good. It's not going to work in practice. Okay? Many of you cannot deal with this here. What's the charge of the oxygen? Negative. What's the charge of the sodium? Positive. How many lone pairs on the oxygen? This is no different than here. I could have just showed this same way. It's O minus. See, up here I did not show the spectator ion. Down here I showed it. And I did not show it with charges. You don't always have to show charges. Just like if I showed sodium chloride, I can show it like that. You know that's Na plus Cl minus, right? Well, we can also show that, and that's Na plus OH minus. Well, guess what? Then you can put R groups here. And just show it like that. That's Na plus O minus, but there's more to it. Na plus O minus and more to it. All right? The reason I point that out is because I always see these little things cause so much problems. Because you guys just tend to gloss over these things, but then when you come to test, you're like, what is that? And it causes you just to miss the whole problem. Always focus on the details and everything that looks a little odd. Because you don't want to get to the test and then realize you don't know a detail. And I probably purposely showed you these different, so you can see things shown different. You never know how you're going to see it. But it's the same thing. We need a stronger base. Well, you can use sodium. What's the charge of the sodium here? It's neutral. That's just sodium. There's nothing else. It's sodium metal. We used it for the sodium and ammonia dissolving metal reduction. It's actually not called a base, but it will do the job. If you react an alcohol with sodium metal, you will get the sodium alkoxide plus hydrogen. That's the fate of the H here. This is actually a redox reaction. So it's not a traditional acid-base reaction. I'm not going to show any acid-base mechanism. The sodium, does it have a lone pair? Can it take the H? It's not an acid-base mechanism. It's a redox reaction. But it's a redox reaction that gives us what we're after here, the oxygen minus. And over here, the charge of the sodium is what? Positive. So it went from oxidation of 0 to positive. The sodium got oxidized. That means something had to get reduced. Actually, the H got reduced because here you consider this as, even though it's covalent in terms of redox, you consider that as H plus 1. But now the H's are what? Elemental, 0. So it went from +1 to 0. That is a reduction. So if you formally assess this, you will see that it has redox. If you take sodium and put it into an alcohol, it will start bubbling. What are the bubbles? Hydrogen gas. Put a balloon over the flask, the balloon will inflate. Okay? And the balloon will float away. If you put a lighter to it, it will explode as the hydrogen gas explodes. Okay? This is a way to generate alkoxide. Now some people also make hydrogen this way. Like you need some hydrogen, we'll take some sodium and put it in an alcohol and you'll create some hydrogen. But here we're after this. You can also make your alkoxide using sodium, what do you want to call this? Charge of the sodium is plus. This is H minus hydride. This is called sodium hydride. You guys have probably never seen this. It is possible. You can have an H minus. And the H minus will act as a base. Now we can do a traditional acid-base reaction. If these electrons bond to the H, these stay behind, what do you get? Doesn't this give the O minus? Sodium sitting with it. So what did we make here? This also produces hydrogen. But this is a traditional acid-base reaction. So, you can't use hydroxide here, but you can generate the alkoxide these other ways. Now we can do a reaction. You take this alcohol, treat it with sodium, you get the alkoxide plus hydrogen. We throw in a carbon with a leaving group, and bam! SN2, we made this bond. Yeah? We alkylated the oxygen. This oxygen has one alkyl group. Now it has two alkyl groups. What do you call the product? We started with an alcohol. The product is a ether. Okay? And when you alkylate alcohols or phenols, we'll see that in a minute, it's called a Williamson ether synthesis. This is a common way to make ethers. And this is probably our first synthesis that is a proper name. Well, actually not. We had to deal with all the reaction. Williamson ether, way to make ethers. Diels-Alder, you're making what? You know sort of that mechanism, but what can you say what product the Diels-Alder gives? It can actually be quite diverse. Well, what's the core structure of a Diels-Alder product? It's going to be a cyclohexyl, right? Okay. Williamson ether synthesis. Williamson, I think, was an English chemist back in the 1800s. Started making all these ethers by taking alcohols and creating them. Okay. And diethyl ether became used as an anesthetic. I don't know if he was the first one to make diethyl ether or what. All right. So what are we doing? We're generating the better nucleophile from the neutral. This is not a good nucleophile. The acid-base reaction, well, the redox generates the better nucleophile. Now we can do the SN2. What about phenols? Phenols, you can use sodium hydroxide, because what's the pK of a phenol? Now 10, hydroxide is going to give this plus 16. Which side's favored? 16. So here you see the reaction's favored by 10 to the 6, and that's enough. As long as it's favored about 10 to the 2 or 10 to the 3, it's good. You can use hydroxide with the more acidic phenols, just not with regular alcohols. And so we can treat phenol with some hydroxide, or potassium hydroxide, or a million and one other bases. Make the sodium phenoxide, and then we can come in here maybe with methyl iodide. Let's get rid of this, right? And these electrons attack the carbon. This is not good for a mechanism. We really need to show this, at least maybe like this. Show that bond there. This attacks the carbon and kicks off the iodine, yeah? Now the oxygen is bonded to the methyl. Showing it sort of condensed over there. And then what else are we going to generate here? Try to balance all this out, right? Sodium iodide. Yeah? That is the spectator ion teamed up with the leaving group. Methyl iodide is a very common source of the methyl there. It is a liquid. Methyl bromide is a gas I told you about. It's harder to use. So with the CH3, you usually always see the iodide as the leading group. Because it's a liquid, it's more common to convenient to use than a gas. Can you make rings this way? Well, yes, you can. You take this alcohol here, which has the halide as well, treat it with sodium, you make this ring. Plus sodium bromide plus hydrogen. What's going on here? Right here's the beginning. What does sodium do to an alcohol? You could say deprotonate, but that sounds like an acid base. It essentially deprotonates. Just be careful with, I reckon that works, but to me it sounds like acid base. This is redox. It makes the minus right plus hydrogen. And by the way, I did not balance that reaction. Anybody wondering about that? Back over here. How do we get two H's when we only have one H on this side? Well, you can balance it. Two of those, two of those, two of those. Is that balanced now? Two sodiums, two H's. You see? Now that's the, you guys, that's the first time I've ever balanced two reactions in one class, one course. I told you I'd only do it one time. It's actually the second time I've done it, if you kept track. Okay? I promise not to do it again. But again, you got to balance it if you want, because you got one H over here. How'd you get two? Well, you balance your reaction. But again, you've already got it there, right? You make the minus. What can that do? These electrons can come right over here, and whoop, SN2. What does that give? It's going to give that. You keep track of your ring. This oxygen is bonded to this carbon. That's 1, 2, 3, 4, and then the oxygen again. 1, 2, 3, 4, and then the oxygen again. You see how rings are put together?
I have a question. If we're showing this mechanism, we just show it like this, or do we need to draw it the whole thing?
Well, the sodium deprotonate, or I would say conversion of this to the alkoxide, we didn't show a mechanism. Because that's redox. And redox are probably radical reactions. We did not show a mechanism for the reaction of an alcohol with sodium. And so no, you would not be expected to show that. Really, this is sort of, do you understand what's going on? We make the alkoxide, and then you see how it's intramolecular SN2. These are quite common and possible. We had a leaving group right here in the same molecule. Yeah. Okay. Synthesis. Can you go backwards? Can you provide a Williamson ether synthesis for this molecule? Show us synthesis. How would you make that compound? And one below. Why don't you work on the first one as we take a 2-minute break? Okay, guys. What is a Williams and ether synthesis? Involves what reacting with what to make the ether? Well, that's how you generate one thing, and that thing reacts with what? That's how you generate the alkoxide, and the alkoxide reacts with what? Yeah, it's the compound with the leaving group. We can call that the compound with the leaving group. We can call it the electrophile, because it's the thing that the nucleophile reacts with. Nucleophiles react with electrophiles. That's how we're making a nucleophile carbon bond. And a couple of weeks ago, I gave you a page that showed 2 ways to make nucleophile carbon bonds. One of them was nucleophile attacking carbocation. But you can do that with substitution. That's going to be an SN1. The other way is for a nucleophile to attack a carbon and kick off a leaving group. And that's SN2. Now in that handout, it does not say SN2. Or maybe it does. Maybe not. Does it say SN2? No, that's not the... No, I'm talking about it probably, I think it's a blue handout I gave you a couple of weeks ago when we first told you it's one of the most important handouts we have. Is it green? It's green. Yes. Did I say SN2 on that page? No, I only called it backside attack. That's because we were not ready to call it SN2. Now we're calling it SN2. Okay? And we actually did some SN2s during our alkene reactions. Okay? Because didn't we make ammonium ions? Maybe, yeah. And didn't some other nucleophile, maybe another bromine? Did they come in here and attack? Which carbon is it going to attack? This one, right? Kick that off? I didn't call it SN2, but what is that right there? It's SN2. We're attacking a carbon, kicking off the leaving group. Okay? That's what we're doing, but that page, all right. Nucleophile. Why? That bromine is very, like, I need some electrons, bad. So this bond is very polarized. There's lots of partial plus here for the nucleophile to be attracted to. Okay? Yes, that page, what color is it? Is it green or blue?
Green.
Yeah, very important. The alkoxide has to be generated, and the alkoxide reacts with something with the leaving group. What's the most common leaving group? Leaving group types? Halogens, not F though. So a lot of times we maybe said it reacts with alkyl halide. I mean something with a leaving group. But it can be other things. It can be a tosylate leaving group, right? So, what type of bond is formed in the Williams and ether synthesis? The O-carbon bond. But which bond do you want to form? We could form this bond. If we did, that would go back. This is a retrosynthesis arrow. This sort of double-lined arrow. We're going backwards. Retrosynthesis. Go backwards to what? Let's go back to this O minus plus what? That would have to react with what to come this way? Propane? Would those two react? Did we go back to the starting materials? Stap plus propane? Now we can come forward. Did we go back to the right two? It needs a leaving group. These two are not going to react. There's no leaving group here. There's no chemistry here. Okay? But if we put a leaving group here, now will those react? Yes. Now we can envision this reacting where? Right there. And kicking off. And will that give this? Should. So yes, we went back to something that is reasonable. We'll call that the A. A. Could we go back to some other O minus and carbon with a leaving group? Maybe we could make this over here instead. Let's call that B. And that would go back to what? Show those. What would be the start materials to make the B bond? That plus what? That plus cyclohexane, yeah? And the oxygen will just magically bond to this carbon by some unbeknownst mechanism? H is not a leaving group. And H is not a leaving group. We looked at all possible leaving groups. You need a leaving group here. What's your favorite leaving group? I'll put bromine over here. How about something different? Chlorine, yeah, but which is better, bromine or chlorine? Bromine's better. Chlorine will work, it's just not as good. Iodine is better, yeah. Iodine is better than both of these. But that's possible here, because this could come in here and kick that off. Would this mechanism give the product? Yes, we proposed two different theoretical approaches. Two different Williamson ether. They're both Williamson ether synthesis because they come from the alkoxide and the carbon with the leaving group. Question is, which is best? Which will give the best yield? The answer here has to do with the carbon with the leaving group. That's secondary carbon. Over here, this is a primary carbon, which is going to undergo an SN2 the best. Primary, less sterics. Okay? This is best. Primary. Now, you could argue something else. I'm not going to open up that can of worms. That's the main thing to look at. Actually, in this particular case, either is kind of okay. In other cases, you may look at one route and say, no, that's not going to work for this reason. All right? Now, how do you generate this here? If you were asked to start with all neutral molecules, can you make this from a neutral molecule? Well, or let's come over here, since this is the best. Let's finish this up. Yeah, this comes from the OH, and how would you make this? Reacting with sodium metal. Or, by the way, you could use potassium metal. That will work too. Probably any of the group of metals will work. Sodium is most common here. So there's your synthesis. You take cyclohexanol, react with sodium to make the alkoxide, then you come in with 1-bromopropane, and you do your SN2, and you did a Williamson ether synthesis of the target molecule. We started with considering a retrosynthetic approach. We're like, okay, how can we go backwards here? And we kind of, okay, we'll use this arrow, you should see that type of arrow. Retrosynthesis. When you do synthesis, you don't just look at this and start here. It's easier to go backwards. It's like retro-engineering something. Start with the end product and just go backwards each step. Then you arrive at the starter. All right? We'll do more of that. You can do this one on your own down here. But again, we can make this O carbon bond or that O carbon bond. Sulfur, which is below oxygen. Can you do this chemistry with sulfur? Yeah. Can you show a product of this reaction here? Same chemistry as oxygen. What's the name of this functional group here? Thiol. Anybody, another name? I reckon that's good enough. If this was an OH, it'd be a phenol. This is often called a thiophenol. Okay? And thiophenols are more acidic than phenols because you'd rather make it a minus on S than O. S is bigger. Actually more acidic. We can deprotonate using hydroxide. In this case, I use lithium hydroxide. What does the lithium hydroxide do to the phenol? Deprotonates it, makes it a minus. Why don't we just do that? That's what that's going to do. Lithium plus S minus. Then we throw in this carbon leaving group. What do we get? Nucleophile attacks carbon, kicks off leaving group, and what do we get? Well, we can show this just like this, but instead of this carbon bonded to a bromine, what is it bonded to now? Sulfur, and the way I drew this, now I gotta, the sulfur is bonded to an aromatic ring. Everybody agree? And next door to the sulfur is a nitro group. Everybody agree? And we just made that bond right there. There's your product, right? Used to be a bromine bonded to this carbon, now it's the nucleophile. We just did a substitution reaction. And that's an example of using sulfur instead of oxygen. It's the same chemistry, it's the same group. Sulfur is more acidic. I mean, SH compounds are more acidic. And the thiol has been converted to a what? What do you call this functional group? Thioether? Or sulfide? How about nitrogen? Nitrogen. With nitrogen, we do not need to make the anion because a neutral nitrogen is a good nucleophile as is. Neutral oxygen is not a good nucleophile, but a neutral nitrogen is. We can do a alkylation of nitrogen. We can actually turn over here. Very back, nitrogen. There's two different ones. Here's one here, 43 to 44. What's going on? Is that a good nucleophile? Well, let's assess this here. We have two neutral nitrogen. Which one's the better nucleophile? tertiary nitrogen or the secondary nitrogen?
Secondary.
Yes, more sterics over here. Yeah, and indeed, that's what's reacting. Is it a good nucleophile neutral, or do we need to make it anion? It's good as is. Good nucleophile, anions, or sp3 nitrogen. sp3 nitrogen, good nucleophile. Carbon with a leaving group. Is OH a good leaving group? It can be. How do you make it a better leaving group? Protonate with strong acid? There's no strong acid here. So it's not a leaving group. But that is, because you don't need to protonate a halogen for it to be a leaving group. Kick that off. What do we get here? Nitrogen now bonds to the carbon. What happened to the H here, though? Did it magically disappear? No, it's there originally, and that's a positive now. And that's what you get originally, but a base has to remove the H. Well, that's triethylamine. Okay, sometimes abbreviated TEA. Nitrogen with 3 ethyl groups. It's acting as a base in this reaction. It takes the H and leaves the electrons behind. And that gives the product shown before I drew it. Okay? The neutral product. What is TOL? Anybody have a guess at what TOL is? You may have used it before. Toluene. Did you use it in lab yesterday? Today? Today you will use toluene? That's an unusual abbreviation. Usually it's abbreviated a little bit another way. 12 hours. Okay. That's an SN2 with a nitrogen. This is a direct alkylation. We're directly alkylating the nitrogen. We may look at the other at top a little bit later. Let's go back to the handout. Although you can do this, direct alkylation has a potential problem. And that's polyalkylation. Overalkylation. And by the way, this is just ammonia. Ammonia is pretty good nucleophile because they have no sterics, neutral nitrogen. This can react here, kick off the leaving group. And by the way, it doesn't matter which is on the line and which is over here. I could put ammonia over here and the alkyl bromide there, right? No difference. Okay? You got to assess what reactivity you have. It doesn't matter where they're positioned yet. Does this give that? Yeah, both pairs, yeah. Here. Now there's no base here like triethylamine. Or is it? Remember previous page, we went positive and then triethylamine removed the H. Okay? Tree with a base, you can remove the H and then you have your neutral product. Problem is, something else can happen. Ammonia can act as a base. And instead of it doing that, it can say, it can come over here, let's draw one of these H's out and change that to 2. How about that? And ammonia can come over here and take an H and leave these behind. What would that give? That's what I'm doing here. With ammonia, we can get this. It gives you your neutral amine, just like up there, but then it makes what? Now the ammonia has the H. and it becomes ammonium, and the Br minus is still here. But this becomes an equilibrium, and neither side is really favored. At this point, though, this can now act as a nucleophile again. And it can come in here and do it again. And this means multiple things are going on. But that would give a positive nitrogen, you could lose an H, but that's how you end up with two alkyl groups on the nitrogen. But guess what? With ammonia here, it can free that up, and this can alkylate again. Okay? And it can keep going. And that's called polyalkylation.
So would that third one make triethylamine?
It actually would make triethylamine, yes. Yeah, but then you might have three alkyls. But it can keep going. This is possible. It doesn't always happen. It depends on the conditions. You know, on the very last page, they apparently were able to do the reaction and only get one alkyl group added to the nitrogen. They don't give a yield here. Actually, they do. They do it a pretty darn good yield. Perhaps because this could alkylate again, but see, it's tertiary here. And how easy will a tertiary amine alkylate again? Maybe not that easy, and so maybe that's how they were able to get a good yield. In the end, polyalkylation can be a problem. Any questions about this sequence here? See what's going on? This reaction goes 10%. You got 10% of this and still 90% of this over here. The ammonium, you can't tell the ammonia, hey ammonia, only do the SN2. Because ammonia will start coming over here and reacting with that product. You can't stop that. The ammonia won't listen to you. Right? It's going to go over and do that acid-base chemistry as well. And that's how you end up with this. Because, can this act as a nucleophile? No, it doesn't have a lone pair. So if it just stayed like that, you would not polyalkylate. But it doesn't stay like that because ammonia comes over here and deprotonates it and makes it neutral again. Now it can continue on. Okay, that is a possibility. There are alternative approaches to direct alkylation of nitrogen, such as using azide. This is called sodium azide. What's the charge of the N3? Negative. When we were doing Lewis structures, one of the problems in my workbook asked me to give structure of azide. Lewis structure. If you do a Lewis structure of azide, it looks like this. Every atom is charged. What's the net charge of that? Minus. And so one sodium plus sits with it. You see a nucleophilic atom there? The N nitrogens are both nucleophilic, not the middle one. So what happens is one of them reacts, and then that gives the product. You're just putting an alkyl group there. That nitrogen becomes neutral, and this is net neutral. This remains like that in the product. Altogether, it's N3. Okay? You should know structure of the azide. But this will not react again. Even though there's a negative nitrogen over here, it's really quenched by the withdrawing. There's no resonance here because you can't make a bond here. The third one over here, this is not nucleophilic. You get a good yield of this. Then with hydrogen, you can actually cleave off two of the nitrogens and you can make a primary amine here in good yield. I'm not sure if nitrogen is the other byproduct. You can make a good amine here in yield. We're up here, where we were trying to make this, we may not get a good yield because we may get polyalkylation as well. This is called an indirect approach, or alternative approach. As you go along in organic, particularly in organic 2, you'll see other ways to alkylate amines. C, synthesis of quaternary amine salts. What's going on here? This attacks here, takes that off, SN2, right? Is that the product shown over there? Can that nitrogen go neutral by losing an H? No. There's no H to lose. So it's not going to readily be able to go neutral. What type of an amine reactant here is a nucleophile? Primary, secondary, or tertiary? Can tertiary amines act as nucleophiles? We said they're going to be sterically hindered. Triethylamine acts as a non-nucleophilic base. But I also told you that they could. It's like a non-stick pan. Something may still stick to it. Okay. Now this reaction I showed heat may require some heat. This is a common reaction. And what did we make here? This nitrogen now has 4 alkyl groups. So is it primary, secondary, tertiary, or it's quaternary? It's a quaternary amine salt, or sometimes called a quaternary ammonium salt. These can be made. Yeah.
So if we were asked to draw out a mechanism for that without the product, would we assume, because of the tertiary nitrogen, would we assume to use it as the base, or as the nucleophile?
For SN2, yeah, just like I showed. Are you thinking another mechanism?
I don't see another method. That'd be the only method you can go with. But because it's, I know you said it's just non-stick. So basically, if there was another mechanism to go with in the same, like in your beginning, if there was another mechanism to go with, would you automatically assume that that's the one you start with?
I need you to clarify the question. What other mechanism? In many cases, you may have to consider multiple mechanisms and decide which mechanism is correct. But I'm wondering, what other mechanism are you considering here? That's where we need to talk about it later. Cover more details. What are you thinking? Okay. Because right now I see no other mechanism, but I want to know what you're thinking. Are you seeing another potential mechanism? Let me know. Quaternary ammonium salts are used. This is a quaternary ammonium salt. It can be made by such a reaction. They're commonly used as antibacterials, topical antibacterials, hand sanitizers. These things often contain ethanol, which is an antibacterial, but they may also contain a quat. These are colloquially called quats. I know over at the YMCA on the wall they have these sanitizers. Wash your hands while you're lifting weights or something or working out. But I read it one day and it said contains, guess what? Didecyl dimethyl ammonium chloride. That right there. Over at the Y. You can go get some on your hands right now. Okay? And that's why I included it in my handout. These are often used as antibacterials. Something about the ionic nature disrupts the cell membrane, or bacteria have cells. Whatnot. Something. Okay, you guys know better than me. But they can serve as antibacterials. Also in biochemistry, you'll see choline.
And choline is an alcohol, but it also has a quat here. Quat near ammonium. All right? You guys familiar with choline? You can put an acetyl group on this and it becomes what? Acetylcholine? Or some people say acetylcholine? Okay. Acetylcholine just has an acetyl group, but it has the quaternary ammonium there. All right? So quats. And here's an example. There's a book called The World Records of Chemistry. Okay? And in that you can find the world's most bitter compound. That's it right there. It's a salt. Now, it's a big salt. Both ions are organic. You see that? Where this salt, both ions are not only, they're not organic, they're just atomic. Two atomic ions. This is two huge organic molecular ions, but it's still a salt. But the cation is what type of compound? A quat. And that's known to be the world's most bitter compound, at least when I put together this handout. I don't know if anything's passed it. How is it used? It's added to things like antifreeze to keep pets from drinking it. Pets like to drink antifreeze and then it's not good for them. Okay? But if you put this in it, they start drinking it. Because antifreeze is usually it's kind of sweet. It tastes good to animals and small children. Okay? But you put this in it, they drink it like, oh, I'm not drinking that. It's so dang bitter. So that's a use of this compound. And that's organic chemistry. We can make compounds and use them for different purposes, including drugs. So that's a quat. Quats can be made by alkylation of tertiary amines. What about carbon? Can we use it as a nucleophile? I did have a cat one time that we're pretty sure died because of antifreeze. A lot of times people poison cats that way. They'll put out antifreeze in the yard or keep the cats out of the yard. And I think we had one a long time ago. We found him dead in the backyard. I think he drank some antifreeze somewhere. Otherwise, he was quite healthy and didn't have a mark on him. He seemed like he was poisoned. His name was Rocco. Yeah. He had an underbite or something. His teeth were like this. Just a little bit. You look at him, look at him. He was a good cat. Cyanide. Well, first tip here. Alkynes. Remember we made acetylide anions at the end of test 2 material? I told you we'd use them a little bit later. Okay. Well, here it is. How can we deprotonate this? Can we? What base did we use before? N-butyl lithium. Remember these bases? Or what other base did we use? NaNH2, this was the handout that has the minus comment. Okay. But we made the carbanion here. It can be made because it's sp. Now we throw in a carbon with a leaving group, and can we do chemistry? Yeah? Can you show the product there? I'll let you show the product on your own. We're about out of time. I don't want to kind of get into it and run out of time here. What's next? Cyanide anion, we mentioned cyanide, yeah. Remember cyanide? And cyanide has what? A carbanion, right? It acts as a nucleophile. These electrons attack here. Take that off. I'll let you show the product there. In both of these examples, we have stereochemistry. What do we know about backside attack? Okay. Yes. I don't know if you hear it described like that. But you're exactly right. The umbrella does what? Inversion. Yeah, inversion. You can go with umbrella effect if that works. Okay? But ultimately, you're going to have to put something on paper to be graded. So let's practice putting these products on paper. And we'll see how you did tomorrow on these. Okay? But again, stereochemistry. Next here, proving mechanism by regiochemistry. Look down here. We take this alkyl bromide and just heat it with ethanol. We can get a reaction. And actually, 2 regioisomers are formed, plus HBr. Can you show mechanism of this reaction? Okay. Think about this, try mechanism here. One thing we want to do is assess, is this a strong nucleophile or weak? Well, the only thing here, that's the carbon with the leaving group, is this must be the nucleophile because the oxygen is replacing. Okay, yeah. Strong or weak? What's a strong nucleophile? Anions or sp3 nitrogens. Okay, listed in the handout. Right? Strong or weak? Okay. So you have to assess what you got here. Reactivity of your reactants. Is this an SN2? What type of nucleophile is required for SN2? This is also in the handout. It may have come with some exclamation points, so I can't remember. Okay? But guys, this is the questions you need to ask when you assess reaction. What mechanism does this seem to be? Once you determine that, then do the mechanism. All right, we'll pick up here tomorrow after the quiz. We'll finish up this handout, yeah? We'll be moving in questions. There's lots of questions at the end of this handout. Okay? Lots of homework questions in the end of this handout. That's what we're asking you on the quiz. There may be a intro type question about SN1 or SN2 on the quiz. I'll try not to have like a lot of stuff for today, but just the intro concepts.